Hi everyone, this last video we're going to be looking at probably the trickiest part of the vectors units, and that is closest approach. So working out these problems where we've got two moving objects and we're going to try and work out whether they collide, if they collide, when they collide, where they collide, and this one here, if they miss each other, what's the closest that they're going to come to each other. Now this approach, we're going to use the scalar product to get this problem done. We did it a different way, and I'm going to show you two different ways of doing this problem that I've got here, but I want to show you a new way, which is using the idea of the scalar product. So here I've got two objects, A and B, they're moving along here, and we want to try and find out when are they closest. Now if you look at the equations, you see I've got t in both equations here. So here's the equations of the line. So RA is the position vector of A, any point on the line A, and VA is the velocity of object A. And similarly over here we've got RB and VB. So the position vector of a point on the line B and V for the velocity of the object B. Now if you look at it in two dimensions like this, you'll say, well, those two lines have got to intersect at some stage. Well, of course they will. But will they intersect at the same time? And that's the thing here. We might define the way that we define these two objects and where they're going. It might be that A and B, the point where those two lines there intersect somewhere off in the future, it might be that A gets there at t equals 3 and B would be at that point at t equals 4 an hour later. So sometimes it's a bit confusing to people to talk about in two dimensions, two objects, and what's the closest that they'll get to each other, when if you're looking at just on the page like this, those two lines are going to intersect, but it may be at a different time. So I hope that makes sense. So let's work it through here. Of course we know that the distance from A to B at any time is B minus A, where the B is the position vector of B and A is the position vector of A. So I'm going to form the equation of, or the distance between A and B at any time t. So the position vector of any point on B is just that. That's just any general point on B is RB plus TVB minus the position vector of any point on A. So that's the most general way that I can write the distance from A to B at any time t. So let's start by tidying that one up a little bit. So I'm going to make that RB minus RA. So let's just identify the positions first, and then we can say plus T VB minus VA. Okay, so remember this is telling us the distance, or the vector, going from A to B, and I'm trying to find what this minimum is going to be. Okay, now we know from our work on relative vectors that RB minus RA is just the position of B relative to A. Okay, it's really just the vector from A to B. Okay, but that's the position of B relative to A. And over here, similar thing, VB minus VA is the relative velocity of B from A. So it is the velocity from A to B. So we write that's the relative from B to A. Okay, now what do we know? We know that if AB represents that vector, and if we want to make that distance, as we want to make the distance between those two, we want to see when is that distance going to be equal to 0, really. We want to see, are these two things going to collide? And if so, you know, when is that collision going to happen? So we want to know when is that going to be 0. It'll be a rearranging of the formula. I'm going to take this over here. So negative T V BA is equal to RBA. And we know that if I just swap around the vector from going from B to A to B, then that will just be a negative vector. So on the left hand side, I'm just going to make this VAB. Okay. So when two objects are going to collide, they are going to satisfy this formula here. Now this is really, really handy, guys, when you're solving these problems, to keep that in mind. In addition, we know that if we want to find the minimum distance between two moving objects, this formula here is the one that we want to use. So this formula over the left is helping us to find when the conditions under which two objects are going to be intersecting. This one on the right helps us to find the minimum distance. So RAB is the relative vector from A to B. Notice it involves time because at time t that will always be changing. And VA to B is just the relative velocity from A to B. And notice that doesn't involve t because if the two objects are travelling with constant velocity, then VAB will be constant the whole time. So that formula on the right is the one that we're going to use to find the minimum distance and the time at which that happens for two moving objects. Here we've got two ships, the Alabama and the Baltimore. We've given their positions and their velocities. Speeds are kilometres an hour, distances in kilometres. If they continue on their respective courses, find the shortest distance between the ships to the nearest 10 metres and find the time at which this happens. I always like to write out, so in this case we've got A and B, that makes life a little bit easier. So let's look at, for ship A, the equation of that line is just going to be 10, 5 is where it starts, that's the point on the line. And it's moving at velocity -2, 4. So if I generalise that, I've got 10 minus 2t for the x coordinate and 5 plus 4t for the y coordinate for that ship. Okay, let's look at ship B. We've got starting at 2 minus 1 and it's going at 2, 8. So in general we've got 2 plus 2t and -1 plus 8t. Cool. Easy? Right. So what's the vector? The relative vector R to B. Remember, I'm going back to this formula here. So RBA in this case, or I could go RAB and VBA. It doesn't matter. So let's go RAB. Okay, so what's RA to B? So that is the position vector of A minus the position vector of B. So we're saying 10 minus 2t minus 2 plus 2t. That's for the x coordinates. And 5 plus 4t minus -1 plus 8t. Okay, this is the position of A relative to B at any time t. So a bit of working out here. 10 minus 2 is 8. -minus 4t. I'm getting this right. And 5 minus -1 is 6. 4t minus 8t is -4t. Looks good to me. Okay, so that's the relative positions taken care of. Now we want the velocity. So we're going to do VBA. Notice I've swapped them around here. So the velocity of B, let's just look at it now. We're just focusing on the velocities, okay? So just these bits here. So that's 2, 8 minus -2, 4. And that gives me 4, 4. All right, cool. Now, we're going to say that the dot product of those two things there is going to be equal to 0. That's what we're looking for. If the dot product is equal to 0 there, that's going to be the time when these things miss each other by the shortest amount. So we want 8 minus 4t, 6 minus 4t, dot 4, 4 equal to 0. Cool. Now we just have to find the value of t. So we've got, for the top one, 32 minus 16t plus 24 minus 16t is 0. Easy. So we've got 56 minus 32t is 0. So 32t is going to be 56, and when we do that division, 56 divided by 32 is actually 1.75. In this case, the unit is hours. So these two ships are going to be closest together when t is 1.75 hours. I can now go back to either one of A or B and find what the position of A and B are at that time when 1.75. So for example, I could put 1.75 and I could put it in there, and that would give me the position of ship A, and I could also do the same for B. But what we really want to know is find the shortest distance between the ships. So this vector here is telling me the distance between the ships at any time t. That's the vector from A to B. So I want to substitute 1.75 in there. Okay, so A to B. So the vector is 8 minus 4 times t, and the bottom vector is 6 minus 4 times t. Okay, so when I do that, I get 1, -1. Okay, that's the vector at that exact time. That is the vector that will take us from point A to the point B. What's the length of that vector? The length of that vector is nice and easy. Square root of 1 squared plus -1 squared. So it's the square root of 2, or approximately 1.41 kilometers. Okay, 1,410 meters. So there we go. It happens at 1.75 hours, and the shortest distance is 1.41 kilometers. Okay, that's the first method. Here's another way of doing this. I'll draw a line under that, change colour. Imagine now that we've got down to the point where we know the relative vector from A to B. And I know what that is. 8 minus 4t, 6 minus 4t. Another method of finding it is finding, well, what's the length of that vector? And let's find the minimum value of that length. So the length of this vector from A to B is just going to be this. It's the square root of each component squared. So I'm kind of using Pythagoras' theorem here, right? There we go. That will be the distance, 8 minus 4t squared plus 6 minus 4t squared. Okay, so let's say that the distance squared, I'm just going to square each side. Now, if you expand all of this out, you get 100 minus 112t plus 32t squared. You can check me if you like, but that's what you get. So you could use your calculator. This is typically in the calculator section. Expand those two out, and that's what you get. So the minimum distance is just going to be the same as the minimum distance when d squared is minimum. Okay, so rather than doing some calculus on this line here with d, which is a little bit tricky with the square root, I could just find, well, what's the value of t that minimises d squared, and hopefully you can see that that same value of t will minimise d. Okay, so I'm going to do a little bit of calculus here and say the derivative of d squared, this is really shorthand, is negative 112 plus 64t. Okay, and if you solve when that equals 0, you'll see you also get 1.75, and in this case it's hours. And then we can go back again and substitute 1.75 and find that distance. So there's two ways of finding the minimum distance between two ships, anything that are moving along. We've got the vector equations. There's two methods where you can find the minimum distance and time for those two objects.